Yeah, go back here to CSC Notebooks, Environment, and I'm going to open the other notebook here that's called Advanced Plotting. It's not really super advanced. It's just maybe a step beyond what we've been doing so far. And I think what I'll do is probably go through this a little bit more quickly. There's not too much where you have to type things in. And so maybe we can try to just kind of go through this as an example. And if you want to work through the notebook at your own pace later on, that might be useful. The goal here in this part of the lesson is to produce a set of what are called subplots using the Matplotlib jargon. And in this case, we're going to have plots for different seasons. So we have here in the years 2012, 2013, seasonal temperatures from the Helsinki-Vantaa airport. So there's here winter temperatures, spring temperatures, summer temperatures, and autumn, broken out into 4 different plots. And in this case, you can also see the temperatures have been converted from degrees Fahrenheit to degrees Celsius. Working with the same data that we had before, and I forgot to ask earlier, is this big enough in the back of the room, like the notebook is okay? Yeah, all right. So yeah, working with the same data that we used just a moment ago, nothing we need to do there. So to get started, we're going to import pandas, and we're going to import Matplotlib. And again, we're using the pyplot submodule, so it's matplotlib.pyplot as PLT. All right, nothing fancy there. We can also set our file path like we did before and read in the data in exactly the same way that we did previously, which means all you have to do is run this cell to read in the data file. As you'll recall, reading the data file in doesn't take that much time, but parsing these values and converting them from character string to a datetime object does take a moment, so this will take maybe 30 seconds or so for the data file to be read in. If we were working in the same notebook, of course, we wouldn't need to do this again, but because we're in a new notebook, the data file needs to be read in once again to a variable here called data. And while we're waiting, we can already go ahead and type in data.head here just to be able to see what our data look like once that data set has been read in. So now I have to be patient, which is not always. There we go. Okay, so our data file has now been read in. It's the same data we used earlier, so of course when we do data.head, things look just like what we were looking at a moment ago, which is that we start on the 1st of January 1952 in the data set. We didn't look at the tail, but it goes up until the end of the day on the 1st of October of 2019. And if we, for instance, I guess actually it was not supposed to type this here, but whatever. We've looked at what the first 5 lines of the data set look like. And if we wanted to, we could also print out the number of observations in data. And then because this is an F string, we can put in here len data, just to give you a sense of how big the data set is that we're working with, how many observations we have. So number of observations in data, and then curly braces around the function call for len with the value data there. And in this case, number of observations in data is 931,767. That might give you some idea why it took a moment to convert all of the text values in the data column to datetime objects. It's because we have almost 1 million lines of data that we're processing here. We saw how to do this last week, so I won't make you type it in, and that is to change the name of a column from one thing to another using a dictionary and the .rename method in pandas. So in this case, our dictionary will take our original column called temp and convert it to be called temp F. That's because we'll convert our temperature from Fahrenheit to Celsius. So it's good to rename the columns to avoid any confusion. So data equals data.rename. We've already done this. And now if we just do again data.head to see what things look like at this point, you'll see now that our temp column has been renamed as temp F. So nothing really too fancy here so far, but yeah, we're just getting familiar with the data set. Now, the thing is, you can see already we have missing data here. We see it in the max and the min columns. We don't know about the temp F column because we only see the first 5 lines out of like 930,000. So one way in which we can check out to see how many missing data values we have would be that we could print out in an F string the number of missing data values per column. And in this case, we can, we'll add in this /n here to add a new line character. And what we're going to put in the curly braces here would be data.is_na, which will tell us whether or not a value is missing or is an actual value, and then .sum. So what this ought to do is tell us then for each column how many values are NA or are missing, and then sum them all up rather than just listing true, false, true, false, true, false, whatever. So let's, this is just basically normal text. Here, the /n is going to give us a new line where the output will be then displayed underneath this text rather than at the end of the line. And then in the curly braces, what we have here is data.isNA, parentheses, and then .sum in some parentheses. And I've done something wrong. Data frame has no object is NA. There's no underscore in is NA. Right. So there we go. Now we can see temp F has actually about 3,600 missing values in it, whereas you can see there are vastly more missing values in the other data columns. But yeah, we're missing about 3,600 values here, and we should probably just discard those because there's no point in working with the missing values at this point. So we can do data.drop_na, and that's our way of dropping out the missing values. We're going to give a subset here so we don't drop from all columns. And our subset in this case will be to only use the values in the temp_F column. So we only want to drop a row if there's missing data in the temp F column. And we'll do in place equals true to do this. We've done this already in the earlier lessons as well. And if I run this like that, and then if I was to, for instance, check the number of values that we have now, I'm just going to type this in as len data. And you can see now there's 928,188 values after dropping the rows where there was missing data from the temp F column. And just as a reminder, if we scroll back up here, to begin with, we had, where is it? 931,000 lines. So we've dropped about 3,600 as expected from the data set. So that's good. And this check your understanding thing, I think I will skip this, so you can also skip this because it's a useful thing to do at some point, but maybe not right now. We've got other things we need to save time for. Yeah. The drop NA line, yeah. So yeah, again, the method's called drop NA. The key thing here is to make sure that you set the subset to only drop values from the column that in this case is temp F that's missing values, because if you don't include this, it's going to drop any row that's missing data, and you'll drop most of the data set that way. Yeah. And the other key thing here is that by doing it this way with the in place equals true, you don't need to say data equals drop NA or data equals data dot drop NA, but instead you can just do the data dot drop NA, and in place equals true means it will overwrite what's in data after dropping the values out. So that's a little bit dangerous, but in our case, I think we can safely say that we're confident we know what we're doing, and we'll drop things that way. All right, let's convert Fahrenheit stuff to Celsius stuff so that we can get into actually what we want to do for today's lesson. So data, and let's say temp underscore C in this case. We're going to add a new column, equals, and we'll do parentheses, data, temp F, temp underscore F, minus 32. So this part's in parentheses because we're going to divide the difference between these two values by 1.8, which is 9 over 5, if you're more familiar with that. But we'll just divide by 1.8. We could make a function and apply it, but we have such a simple conversion here that we can just type this in to convert from Fahrenheit to Celsius. We'll take the Fahrenheit value minus 32 degrees, and then once we've done that, divide the result by 1.8. And then if you data.head, you'll see now that we have a temp F column and a temp C column. These temperatures are right around freezing in Fahrenheit, so of course we've got temperatures in Celsius that are also close to freezing in that case. So this again looks like it's doing things correctly. Okay, let's go to using subplots. How do we do that? What's the sort of way in which we will handle putting data onto these different plots within a given figure? For us, what we want to do is we want to have 4 different seasons. So we have winter, which is going to be from December 2012 to February 2013. Spring, which is March 2013 to May 2013. Summer, which is going to be June through August. And September to November will be autumn. Those are our 4 seasons. We're not going to worry about the sort of strict definition of seasons based on when the solstice is or when the sort of equinox dates are, but instead just to say this is close enough for our purpose. I've given you the example of how to do this selection for the 3 of the 4 seasons here, but we can type in the example for winter. And what we'll do is we can make a variable here called winter that's going to be equal to data.loc. So we're going to use that accessor method that we had encountered before to find locations. In this case, we want to have 2 different boundaries here. So we want to have a starting date and an ending date for our seasons. So we would have, for instance, data.index. So this is the reason why I have put these things in parentheses and then an ampersand here, is to combine these 2 conditions together. So data.loc, and then data.index is going to be greater than or equal to, and then 2012. We want to start on the first day of December, so that's month 12. 01 is the day, and then 0000 for midnight on that day. So we want winter to start on the first day of December 2012 in our selection here. Then we want to have our data.index go up to, but be less than, the first day of March of 2013. So by using the less than in this case, we're not going to include March but we'll get every date up to the end of March, which covers the thing that's kind of nasty about dealing with February, which is that every 4 years you have one more day than you normally do. So if we say it's less than the first day of March, who cares if there's a leap year that year or not? We don't have to worry about that. So we could say 2013, March is the third month. First day of the month would be 1, naturally. And then 0000 would be the start of the day on the first day of March 2013. That will give us our selection of values from our data frame. It will give us a winter data frame with that range of dates. And then we would say that our winter underscore temps would be equal to winter temp C. This is just going to make it easier to deal specifically with the temperature values for a given season. So we don't necessarily need to do this. We could also refer to winter temp C later on, but typing in winter temps is a little bit easier. So that's how we're going to deal with things. So that's going to give us our selection of dates. The other 3 seasons, you don't have to type in anything, so you can just run this cell at that point to extract our winter temperatures. And we could then say, for example, AX1, because we're going to have 4 different plots here, would be temps dot plot. So before we had AX equals this, now we have AX 1, 2, 3, 4, just to kind of keep these things separate so that we can refer back to the winter, the spring, the summer, and the autumn plots all separately. If I run this cell, I can now see, for example, what our selection of plot data looks like. So you can see that 2012, December 1st is our starting date. That looks good. First day of March of 2013 is the end date, but I don't actually think we have a data value for that point. It just it puts it on here as the sort of end of the axis range because that's a nice way to see it, since you can see that we're only getting about every 15 days we get a tick on here anyway. So we have our selection for the winter that we made up here, and then we just did this winter temps.plot in order to take a look at what the data look like. So the thing is, that's not a subplot, that's just an individual plot. And if I run the other cells here, I can plot the temperatures for the spring, and it does spring stuff, meaning the temperatures are warming up from the winter through the spring. The summer temperatures do summer stuff, which is basically meaning that they're kind of hovering fairly warm and sort of consistently. And then, of course, in the autumn, as we are now experiencing ourselves, the temperatures start to cool down. So far, things look pretty good. Are there any questions or issues at this point? I've seen a little bit of discussion in the audience, so I just want to make sure there's not anything that's got you totally stuck, because this is sort of relevant for this week's exercise and the final exercise for the course. But okay, if I don't see anything, kind of urgent, then we'll call that good enough. One thing that's common when you want to plot data like this, like if we want to look at the temperatures for different seasons, a common thing you would do there would be to want to plot the data on plots where you have the similar y-axis range to make it easier to compare to see like when is a season warmer than another one. Because you could very easily look at this plot, and if you're not paying close attention to the numbers along the y-axis, the summer plot actually looks a bit like the winter plot. It's not quite the same, but it's similar in sort of its overall style, that the temperatures are not changing a whole lot during that season. So we can find the bounds of our data, for example, here, by figuring out what the minimum temperature is of all the seasons. And then we're going to subtract 5 degrees from that minimum temperature so that when we plot it, we have a little bit of space between the axis and the line that's being plotted. So we could say, for instance, min temp equals min And then what we want to give here is winter temps dot min. So this is going to find the minimum temperature in the winter. Most probably that's going to be the minimum temperature for our entire data set. But so we have this min function is going to find the smallest value out of a list of things. So we have winter temps dot min, we have spring temps. And if you want to copy and paste this down from below, you could just change the maxes to mins. But spring temps dot min, summer temps dot min, temps dot min, and autumn temps. This is going well. Dot min. My goodness. So at that point, we just need to add our close parentheses. So what this min function is going to do is each one of these is going to return the minimum temperature for that season. And then the min function is going to find the minimum among all three, or all four of the seasons, rather. Once we find that minimum temperature, we can take the min temp and say it's equal to min temp minus 5. And again, this is just so that when you plot this, we're going to use this minimum temperature as the minimum y-axis value, and we just want to have a little space between the line that gets plotted and the axis itself so that it doesn't kind of, I don't know, interfere with the plot axis. So this is basically the same thing that's down here, but doing min instead of max. And if you run this, what you'll see is that the minimum temperature, minus 5 degrees, is minus 35, and the maximum temperature, in this case, plus 5 degrees, because we're adding the padding there, is 35 degrees. So our range of temperatures is plus or minus 35 degrees for our seasons. Now, in order to create our subplots, we need to do something we haven't done yet, which is to actually use this subplots command. And we can do that by saying fig comma axes equals plt.subplots. And then we're going to add some stuff in here. So this command is going to return a way for us to be able to reference the figure, which is all of the plots together and some of the elements there, like the size of the combined 4 plots that we're going to put on here. And then the axes, which are the individual plot axes themselves. So this is going to return 2 different things here, which is why it's fig comma axes equals plt.subplots. We're going to say the number of rows we have will be equal to 2. The number of columns, which is n cols, is equal to 2. And then the figure size, which we do with the fig size like we did earlier, and we'll actually make it the same size, 12, comma 8. So fig comma axes equals plt.subplots, n rows equals 2, n cols equals 2, fig size equals this. You don't actually even need to name like n rows or n cols. You could just put 2 comma 2, but just to make it clear how many rows and columns we have, we'll do it like that. If you run this command, what you'll get is an empty set of 4 plot axes. So we haven't put anything on these plots, but that's basically how you create this tiled 4 plots set if you wanted to. If you were really wanting to do something crazy, you could increase the number of rows and columns. It may take a moment because now it's going to produce 64 plots. But in certain instances, you want to have things like a whole bunch of different plots together, and it's of course possible to produce larger numbers of these plots, or to change the number of rows and columns to be different things. So if you want to have 1 row with 8 plots, of course you can do that as well. But for us, we want 2 and 2, so let's stick with that example. Now, one thing that's a little bit cumbersome here is we now have 4 plots, and maybe not an intuitive way for how to refer to those. What you'll see if you look at the output here, I thought that should be output. Right. I need to actually have the axes object output here. So when I add this axes in here, it's going to print out that there's what we have here is actually a list of 2 subplots, comma, and a list of 2 more subplots. So actually we have a nested set of 2 lists inside of this axes variable. In order to refer to each one of the individual plots, it's oftentimes convenient to rename these things so that like AX11 would be the plot on the top left, AX12 would be the top right, AX21 would be the bottom left, and AX22 would be the bottom right. So this is, row 1 and row 2, just giving these names like this. AX11 or 11 is going to be equal to the axes, where we have row is equal to 0 and column is equal to 0, etc. So this will allow us to refer to each one of the 4 tiled plots more directly. There are, again, other ways that you can do this, but this is the sort of typical way in which you'll see examples of creating subplots. If you prefer, you're of course welcome to use the 2 sets of index values to refer to a plot location, but I think most of the time typing that in is more cumbersome than having some other variable you can refer to. All right, let's make our plot at this point. So we need to plot our winter data, which we can do as wintertemps.plot like we did before. What we're going to add here when we do this plot is to set the axes to use as equals AX11. So we're going to put our winter temps on the top left side by using this AX parameter, which will allow us to specify which set of plot axes that things should be plotted on. We can then set the color of the line to plot. I think maybe in this case, winter's cold, we can make this blue. We can set the line width with the LW. So we had set in a variable here a value of 1.5 for the line width. So we just say LW equals line width. So if we want to change the line width on all the plots, we don't have to do that separately. And then we set the Y limit. So Y lim equals, and we'll make it go from min temp to max temp. And these are the things that we had defined earlier when calculating what the range of the temperatures were for the data set that we're plotting. So this will plot our winter temps data on the axis that would be corresponding to the upper left plot panel, set the color of the line to be blue, set its width to be 1.5, and then also set the range of values on the y-axis rather to go from min temp to max temp. So it's consistent with all of the different plots that we have here. The spring, summer, and autumn are already there typed in for you. So all you should need to do once you type in the winter temps plot command is to run this cell. When you do that, what you'll see is a plot that's starting to look a bit like what we teased with at the beginning of the lesson, in being able to produce these seasonal temperature plots where we have winter, spring, summer, and autumn. But there's a couple problems here, as you can tell. For one, you can't tell which season is which. You could look at the dates, I suppose, but it's not necessarily obvious which season is which. So that's not great. In addition, you can see that our plots are kind of overlapping with our plot axis labels. That's not that nice either. And there might be some other things you'd like to have on here, like grid lines, that would make it easier to see some useful reference points like the temperatures and dates and where they fall relative to the data that you're plotting. So we can do a little bit better with this. So what I'm going to do now is basically just run some cells that are already filled in for you because we've done this stuff. So we'll make a new set of new figure and new plot axes, rename them like we just did by running this cell. Okay, that makes our empty set of plot axes. Then we're going to do what we did just above, which was like you saw that we set the line width. We did this winter temps dot plot command. The only difference between what was plotted above and here is that we've also added the grid equals true parameter. And grid is the way in which we refer to the grid lines that are going to be shown on the plot. Then we add this sort of super title or subtitle that goes above all four of the plots that says this is our seasonal temperature observations for the Helsinki-Vantaa airport. And then one kind of little nasty looking thing here, which is we rotate the x-axis tick labels so that they're only rotated 20 degrees from horizontal so that they won't be covered up by the plots. If we scroll back up for just a second to our last plot example, this, I don't know, this is like whatever the default or 30 degrees or something like that, but you can see the plots are kind of going on top of this, so we can rotate them a little bit to not be covered by the plots. Then we add some axis labels, so dates and temperature axis labels, and then finally our labels on the plots themselves to indicate which season is which. So winter, spring, summer, and autumn. You run that, and with just a couple little tweaks there, we end up with the plot that we started with at the beginning of the lesson, which shows our seasonal temperature values in different colors for the different seasons, has nice labels on there and grid lines to be able to look at the data, and that's more or less how you can produce the plot that we started with there at the beginning of the lesson as motivation. Yeah, okay. I think we'll probably, again, skip this check your understanding thing just in the interest of time, but are there any questions at this point about plotting with the subplots or anything that was not, I don't know. I do realize and appreciate that I went through this a little bit quickly. I just want to save some time for introducing the exercise and things like that, so I kind of... Yeah, so space between the subplots, I think it is possible to add it. I can't remember off the top of my head what the command is to add the padding between the plots, but of course it's possible to do that. We could also check and see, like, if we do plt.tight layout sometimes helps with subplotting. It will basically try to maximize the plot space but not have anything overlap. We can see if that helps in this case. It's just kind of like a command in there that, yeah, I don't know that it really changed much in this particular instance. Essentially, it tries to kind of maximize the size of the plots without having them overlap when using subplots. We'd have to dig into the Matplotlib documentation to figure out what the command is to add more space between the individual plots, but it's certainly possible to do it. You just have to search in the documentation. Are there other questions? I mean, one thing I can say, for instance, about the spacing between the plots is it will vary depending on the figure size that you use. So if you make the figure a little bit taller, you can sometimes just, like, that's sometimes the quickest way to get a little extra space between them vertically is just to make the figure size a bit bigger. But of course, you can control all of these things as well. But yeah, were there other questions that you had? So, like, how can I informally assess this? Like, if you feel confident that you could use the lesson materials to do something similar to this again, maybe raise your hand. It's a bit concerning. Okay, so there's a few hands. I don't see people, like, really, like, enthusiastically hands shooting up, but I see at least reluctant hand raising. So the good thing is that you'll get a chance to do this in the exercise this week. So you'll have an opportunity to practice. So it's not necessarily the case that you need to know how to do this right now and sort of, be able to do it on command. The other thing is that there's a lot of useful stuff from the materials from this week's lesson that you can harvest, and I would encourage you to consider the idea that when you do plotting stuff in Python, starting from a working example is kind of the most efficient way to work through things. So like if you're asked to make plots that look somewhat like this in the exercise, go and take a look at how we did it in class, copy and paste that code and start modifying that as your way to start making the plot rather than kind of going back and typing everything in from scratch. I think you'll save a lot of time that way. But if there aren't any more questions at this point, what I would like to do is two things. One is that I would like to note, of course, that as usual, we have an exercise for this week, exercise 7. It is due by the end of the day on Friday next week. So we don't have class, of course, next week, as today is our last class session, but the exercise is due by the end of the day, or well, not end of the day, by 5 o'clock on Friday, end of the working day, I suppose, next week. So nothing sort of surprising there, perhaps, other than you have an extra couple days to finish this. Again, you can work with your partner if you would like on this exercise, and you'll find some hints, of course, for how to do the exercise on the course page. I think Lesson 7's exercise is actually quite light compared to some of the other ones. But there's a reason for that. And the reason is that we also have a final course exercise or final exercise for the course that's in addition to exercise number 7. This is actually not necessarily more work than the course used to be. We ended up splitting off this part of Lesson 7's exercise into a separate exercise and making it an individual assignment rather than working with a partner for this one. I'll talk about this in a little bit more detail when we go into what the exercise has you doing. But the important thing to note here is that it should be completed individually, but it doesn't necessarily mean you can't work together with someone else. It's just that you will be turning in your own notebook. It should be typed in with your own fingers and not sort of copied and pasted from your partner's notebook. So be aware of that. But yeah, we'll talk about that in just a second. Let's take a look at exercise number 7 first, which I think that's hopefully big enough to see. So as noted, first off, exercise 7 is due next week on Friday at 5 o'clock. And we have 2 problems in this exercise. First problem is basically just easing you into making a plot using Matplotlib and pandas by having you produce a little candy plot like this one here. And yeah, that's what it looks like. It's basically just random points that are colored with random colors that are taken from this color bar here. In this case, I think this one's called rainbow. And you'll see that I think this is 1,000 random points that are plotted here as a scatter plot. And essentially, that is your task in the exercise. So we're going to use a library here called NumPy. This is the one that's hiding under the hood in pandas. We're only going to use it because we have to produce 1,000 random numbers to be able to plot these random points. And there is a hint on the course page about how to use NumPy to get random numbers. So we're going to make a data frame called data that's empty, and then we're going to make a column called X and a column called Y that we're going to fill with 1,000 random numbers to be able to have these random points like shown in the example plot here. After you do that, you're going to make another variable called colors, which you'll use to store 1,000 random numbers for that. And then you have the task of using dataframe.plot to make a scatter plot. And you're given some tips here about how to set the size of the points that are plotted, how to use the color map parameter, which allows you to choose the colors that are being used. For example, you can see that in Matplotlib, if you go scrolling through the documentation that's available here, there's a bunch of different color maps that can be used, and you're free to choose one that you like, as long as you don't choose jet. That one's sort of, everybody hates that one, so don't use jet. It distorts data visualization, so there's reasons not to use it, but it used to be the default in Matplotlib and actually in MATLAB as well, but you're advised not to do that because it misrepresents your data. So you pick any other one besides jet. That's the exercise at that point basically is now, then it tells you kind of the other things you can do to make your plot complete. And then finally you should save your plot as a figure file and make sure that you commit both your modified notebook and this image file to your GitHub repository. That's how you're going to go about things in problem 1, and hopefully you can make yourself a nice little candy plot that looks like this. Problem number 2 is not rendered properly, so let me refresh. It's about plotting temperature data, and it's going to be, in this case, about plotting temperatures for monthly values of temperature over the last 30 years from the Helsinki-Vantaa airport. So your final output will look like this. So this is just showing from 1988 to 2000, or maybe, 1988 to 2018 or something like that, the monthly temperatures at the Helsinki-Vantaa airport as a time series. You're given a data file in this case and some information about that data file. So your data file has monthly temperatures, a few different column names, and you'll read that in. I think it's similar to the styles of data that we've used in file formats before. So the first task will be to read in the data file, nothing surprising there. Then you're going to select from the data file the 30-year period from January 1988 to December 2018. So 30-year period to select out of there. And then you're going to go about making your plot. So you're given a figure size to use and some line style tips and some titles and things like that to use. And in the end, you'll then save your plot you produce as a image file. And just like before, you'll commit both the modified notebook and your image file to the GitHub repository. If you're interested, you can also test out using hvplot to make yourself an interactive plot at the end of the exercise. It's not something that will be graded, so it's just if you're, it's for your own interest, but if you want to have an opportunity to make an interactive plot, please feel free to test out using hvplot. Any questions about exercise 7? Okay, final exercise. So this one, normal exercises are worth 10 points. This one is worth a little bit more. I can tell you why we do it this way, and that is because in the past, most people got very close to all of the points on the exercises, which meant that when it came time to do the assessment, we had to set a very high threshold for the boundary between certain grade numbers. In fact, I think there was one year where we had to have a sort of 98% as the sort of threshold between a grade 4 and a grade 5. And it wasn't really convincing us as teachers that we were doing a very good job of assessing how people had done in the course, which led us to then split off things and make the exercise at the end here, the final one, worth a little bit more, and to put you into a little bit more of a position of being given a task with a bit less structure so that we can try and figure out how much you have learned in the course. So, differences here. You're working individually. As I mentioned, that doesn't mean you can't talk with other people, but it just means that the notebook you turn in, the files you commit, the stuff you produce will all be yours, and it should be produced with your interaction with the computer and GitLab and things like that. Another difference in the final exercise is that we are going to give you general instructions for what to do instead of a notebook that is very heavily structured. The idea here is to kind of give you a bit more autonomy to solve some of the problems. The things you're going to do are very similar to what we've done in the rest of the course. So it's not like it's going to be totally coming out of nowhere that you should now, come up with some much more complicated thing than what we've normally done. It's just that we're taking away a little bit of the structure so that you're free to choose how you want to go about solving the problem that you're given. And in this case, that problem is to be looking at weather anomalies from the Sodankylä weather station for the past 100 years or so, because this station has an exceptionally long history of observations. So in being given less structure, you're also given a Jupyter notebook that's empty. So it exists, but it just doesn't have anything in it to begin with. So what that will mean is that you'll not only be asked to kind of code up solutions for how you're going to solve this problem, but you could also provide some documentation, for example, like in the markdown cells, explaining a little bit of what you're doing, which is very much in the way that you would do this kind of data analysis. If someone were to say, like, even if you yourself decided you wanted to use pandas to analyze data for your master's thesis, you probably wouldn't just have code cells, but you would take advantage of the fact that if you're working in Jupyter Notebook, you might as well have descriptive text there and then a code cell and some more descriptive text to kind of walk you through the steps you're using to perform your analysis. In the end, the goal is to produce these temperature anomaly plots for the 4 different seasons: winter, spring, summer, and autumn. That would go from the years 1909 to 2019. I think that covers the whole record of the Sodankylä temperature data that's available. But note, these are temperature anomalies, not actual temperatures like we saw in today's lesson. So that means it's going to be some deviation in temperature from the average temperature that you had. That idea might sound somewhat familiar from exercise number 6. You're doing basically the same thing here using this other data set. And so you'll produce a plot in the end that looks something like this. Of course, in place of these giant words, you'll have data that's plotted. The data you're working with is provided to you in a data file. So we have daily temperature data from January of 1908 to October of 2020. And the data was downloaded from the National Oceanographic and Atmospheric Administration database, just like the other exercises we've worked with up to this point. Get an idea of the data format here. You can see that we have, as usual, something about a station, the station name, date, average temperature, Tmax, and Tmin. What's a little bit weird here is that the T average column is missing data in many cases. So we're going to attempt to deal with that issue by filling in some values. So that's what's noted here, is that many of the T average column values are missing. And so if you have a missing T average value, what we're going to do is suggest that you estimate what the temperature would be by taking the average of the Tmax and Tmin, and not necessarily filling that in and overwriting what's in T average, but just calculating these average values and putting them in a different column. And then at some point, you'll then say, if I'm missing a temperature for T average, instead use this estimated average temperature for that day. It's not a perfect solution because we're kind of, we're doing the best we can in this case with the lacking average temperature data. But you'll see that this will help in providing a longer climate record. So you're then given some instructions basically of like how to proceed with the exercise. I would suggest kind of reading this through carefully before you get started. But the steps are going to sound familiar to you, I think, on some level. So you're going to read in a data file, and you're going to convert missing data values to NA. The minus 9999 in this case is used to indicate missing data, so you'll convert those to NA as we have done in previous exercises. Then you're going to have this operation where you fill in the missing values from the temperature average column with these estimates, as I just mentioned. Then you're going to make a function to convert temperatures in Fahrenheit to temperatures in Celsius. So yes, indeed, when we were looking at temperatures here, it was Tmin minus 37 Fahrenheit, which is pretty cold. Minus 40 Fahrenheit is minus 40 Celsius, so that should give you some idea. It's pretty cold. Minimum temperatures there. So you'll convert temperatures from Fahrenheit to Celsius. Then you'll calculate the seasonal average temperature for each season in every year. So you should have, like, for instance, winter 1909, spring 1909, summer 1909, etc. Using the following months, like we were using in the lesson for today. Then you'll have the step of calculating the average temperatures for this reference period, like we did in exercise number 6, but from 1951 to 1980 in this case, you'll calculate a seasonal average temperature. So you'll have one for each season. Before we had one for each month in exercise 6. So you should have one average winter temperature from this time range, and an average spring and average summer, etc. Once you have those, you can calculate your temperature anomalies, and then finally, you can produce the plot. This might seem a little bit intimidating because it's quite a lot, but it is basically things you've done in lessons 5, 6, and 7, and things that you're variably familiar with to some extent. And so it is a fair amount of work. There's no question about that. But it's also nice in a sense that if you look at the description here, you'll see that this is not due until 18th of November. So you have a little bit of time to do it. We didn't want to force you to use the sort of break week between periods 1 and 2 to do this, because maybe you want to use some of that time for a break. So this is then due, I think, maybe 2 weeks into period 2 would be the due date. You're most welcome to turn it in before that if you want to get it out of the way and things like that. Of course, that's fine, but you have some extra time to work on this because this exercise will be a little bit more time-consuming. It's also part of the reason why we try to make exercise 7 a little bit lighter, because we don't want to sort of have you do a full exercise like a normal week's exercise plus the final exercise. That would be quite a lot of work. But yeah, this is more or less based on the old exercise 7. We've done this for now a couple of years like this way, and I think it seems to be working a bit better. To help you in figuring out how you want to spend your time and invest your energy and things like that, you will find on the course page a breakdown of how the grading is done. So this also should help you feel that, like, we will be objective in assessing how you've done things. So these are the different items that you're asked to do. So reading in the data file, processing the input, etc. And you can find, like, what will give you the kind of full points for that part of the exercise, and how that breaks down if you don't do those things. So, like, if you don't read the data file in, unfortunately, you'll get 0 points for reading in the data file. I suppose that's not a surprise, but yeah, that's how that goes. And you'll see then, of course, how these different things are handled. If you're asked to create a function and use it to convert your temperatures, if you don't do that, you're not going to get many points for that part of the exercise. And so you can see things there. You can also see, and I will highlight, that you can get points for using Markdown documentation, and you can get points for using code comments. These combined are worth about, I think it's a quarter of the points on the exercise. So please don't forget to use Markdown cells and to use code comments to explain what you're doing. But again, I would say you can look through here on your own. You can see exactly what you need to do in order to get the full points for the different parts of the exercise. And hopefully that will guide you if you come to the unfortunate situation of needing to decide how to invest your time to be able to get as many points as possible before the exercise deadline. Do you have any questions at this point? I suppose concerns is probably a bigger thing, but questions I'll ask first. Okay, so I have one other minor thing to mention, and it's still with some uncertainty, but normally in years when we've offered the class on site, I have also requested from GitHub that they send us a little box with some goodies. I have requested that this year. I don't know if it's just slower than normal in arriving here, but it hasn't arrived yet. But normally the goodies include things like little stickers and GitHub cheat sheets and things like that. So given that it's the last day of class and it hasn't shown up yet, it doesn't mean I'm just going to hoard the stickers in my office and never give them to anyone. But it will mean that most likely you should keep an eye on Slack even after the course ends, because whenever that shows up, we'll pick a time and a place and come with the box of stickers, and you guys can come and take your selection of stickers. I do hope it will actually turn up. I haven't gotten any confirmation that it's actually shipped, but in the past it's also been very mysterious that you request it and then it just shows up at some point. So we'll see, but I wanted to at least say one nice thing to kind of counteract all the work I've asked you to do. So just keep an eye on Slack, and please talk to each other, because I know not everybody will be actively following Slack. Whenever this box shows up, and hopefully it does indeed turn up, I'll let you know, and we'll find a time so that you can come and get your goodies. Normally they do provide a nice cute selection of stickers, so you can kind of find one that fits your personality, I hope. So I'm very hopeful that they will actually show up, and I don't want to hype you up and hope and have them not turn up. I'll send a second request if they don't turn up soon. But otherwise, if you don't have any questions or anything at this point, I would just say best of luck with the exercise 7 and the final exercise. Again, we'll have an exercise session tomorrow and on Friday where you can get some assistance from the course assistants. And on behalf of myself and Christoph and the course assistants, say thanks for putting your energy into the course. I hope you find it useful, and we'll be here to assist you in the remaining time before the course ends. For those who are continuing on to AutoGIS 2, Christoph will be the guy who's in charge of that, and that will start in 2 weeks-ish.
1st of November.
1st of November.
And it's in the afternoon.
Yeah. Yeah. So, 1st of November will be the first class in the afternoon. C222 in the Exactum is the classroom where that will be. And I guess he'll see you there in whatever that is, a couple weeks. So, all right. Thanks.